Welcome, everyone. Good to have you all here on Monday afternoon. Um, Today, we are going to have. I'm just going to mute people. So this session is about the data science, especially the data insights in Journey. Before I hand it over to Aruna, who's our speaker, I'd like to talk about who are we and what we do. As you all know, Lean Women in Tech India started in 2018, and I just felt the pulse with Lean Foundation, and the news is that we are now 3,500 women, both in Facebook, WhatsApp, and the LinkedIn followers, plus our subscribed users into our newsletter. So it's a good number that we are growing, and it's also good that we are getting connected with each other. So if you are interested to join the group, or if you are already part of the group, my one point is to make ensure you help other women to join this group. And also, what we do in Lean in Women in Tech India is like we give two upskilling meetups that we do every time. One is the tech meetup, which we say Win Tech series, and another meetup is on self awareness coaching that is required for soft skills for women to grow in the leadership side. So please feel free to let your friends know to upskill yourself. This is the opportunity for you to learn and as well as share. What we are bringing this year is apart from the Vintech series, we are also bringing a new series called Author Spotlight. This is basically for the women who are writing books on women empowerment. So it is for women, by women, and to women. So it is an author spotlight where we want to encourage the book on leadership on women, and also encourage women who write book. So it's a two-way process that we do the author part of it. So this is, I'm proud to say that the VT group is growing, and also would like to hand it over to Aruna, who is our speaker today, and not actually hold you off to know about the data insights journey. Aruna, tell us about yourself before you start the session on data insights.
Yeah, sure. Yeah, I mean, very briefly, so I am a data engineering manager at Infoblox. Prior to this, I worked as a data scientist for close to 2 years. I think in the process, it gave me a very good, grasp as I straddled across the two areas. It was a very interesting journey to see both sides of the coin, so to speak. Prior to this, I have worked in scale and performance in various roles at Yahoo, VeriSign, Nokia. So yeah, I mean, definitely looking forward to the session today.
Thank you, Aruna. We are looking forward for the session, and over to you.
Yeah, thanks.
And
Thanks.
also, I think Shobita, I think you will have to give Aruna the open it for sharing.
Yeah.
In the share screen, there will be allow all participants. Just allow that to happen so that Aruna can stay.
Somehow it's not working for me, Preeti.
Yeah, you can make Aruna the host otherwise.
Okay. Yeah, so I have made Aruna the host.
I'm still not able to share my screen.
Give me a minute.
Yeah, sure. Yeah, I think I'm the host now. Let me quickly share my screen. Yeah. Yeah, so can everyone see my screen?
Yes, Aruna.
Okay, yeah. Thanks, Shobita. Thanks. Yeah, thanks everyone for making the time today. I mean, Monday afternoons, maybe definitely taking the time off from your busy time to join on our journey, the data to insights journey. Um, so to start off, I will go over big data. I mean, the first few slides, I'll be talking of big data, some basics, concepts, like where have we come from in terms of data and the volumes. Then I'll move into machine learning. We'll talk of few of the concepts in machine learning, which we're hearing quite a bit in and around us. And finally, towards the end, I'll be taking up a data set. A data set I've picked up from Kaggle, and then we'll use that to create some models, machine learning insights from it as well. So that's the whole journey that we'll be going through today. To start off, so this is this is a series which comes out from Domo every year. From the past few years, I've been seeing it. And it's very interesting, actually. I mean, what it gives you is an insight into the volumes, the traffic that we are seeing and how it's been increasing over the years, right? So this is the volume, the traffic generated every minute of the day. The particular infographic here is from 2020. And as I think quite evident from this particular year is we're seeing a lot of Zoom, Netflix, Microsoft Teams as well. Of course, the regular Instagram traffic, YouTube is also there. It's what it basically indicates is that all these applications are generating a lot of traffic and probably in essence a lot of data as well. And so what do you do with this data, right? You have so much of volume. How do you handle it? What do you do? Can you analyze it? So those are some of the background questions that that would pop into your mind, but potentially that's what we are seeing here. Yeah, I mean, if you have observed this series over the years, it is very interesting to also compare how the numbers have changed and increased as well. I mean, very interesting thing here is the WhatsApp user messages shared around 41 million. Interesting tidbit is that Indians do a lot of good morning messages. So, if you have ever done messages just to say a good morning, you're actually contributing a big deal to the WhatsApp messaging. So this is just a big picture. We are saying here is the amount of traffic we're generating year by year, and what does it mean to us, right? And when we look at it from a different perspective, so let's say we have all of this data. So you're going to store it and keep it somewhere. This particular infographic is a couple of years old, but the point is pretty obvious. The volume of data we are generating in a day is pretty huge. Like you see that 4 terabytes of data is generated and stored. This is data generated by connected cars. Similarly, 28 petabytes of data is generated by IoT devices. And in fact, the prediction from here is that by 2025, we will have 463 exabytes of data. And these are like really vast, huge numbers, which means you have so much of data to look at, analyze, make insights, or create use cases and applications from. So that's an interesting background of where we have come from and where we are headed in terms of the big data or scale that we are looking at in the future. So just for the, just in case you're wondering, terabyte is, we start from terabyte followed by petabyte, exabyte, and then you have zettabytes and yottabytes. So those are still, units that we have maybe we are seeing it around, but we're starting to see this bigger units more and more in our day-to-day data journeys. Um, so that's just to give a background of big data and how the scale has been changing, right? I mean, I think it's kind of challenging the norms of what big data is, how much is big enough, right? So that's kind of the premise of the first two slides. And if you look at big data, quite commonly you would see it being described or characterized with 4 V's. So the 4 V's, the first V of which is volume. And as we have seen in the previous two slides, the scale is really growing. I mean, the volume and scale that we're looking at is definitely growing, and it will keep growing. So that's the first V we are looking at. Second V is velocity. So velocity is the rate of data being generated. Now, definitely the rate of, like if you're looking at applications like say trading platforms or e-commerce, a lot of them keep generating a lot of data, and this rate at which they're getting generated, the per second, per millisecond data volume is growing as well. In fact, an interesting um, example here is airplanes, aircrafts. So the sensors in aircrafts generate a lot of data, sensor data. And this data is used by companies like Boeing, which do analysis to understand like when is this aircraft coming up? Is it coming up for repairs? Is there any problem? And they also use it to improve their research. So definitely velocity is a big factor of big data that we're looking at. Another aspect is variety. Variety is the different types of data that you have. I mean, looking at structured, semi-structured, or unstructured. So potentially you're saying you could have text, images, audio, video, geodata. I mean, the variety is really pretty large and vast. And the kind of data looking at is also changing. Another interesting aspect is veracity, which talks of the source, right? How much do you trust the source? Do you understand who is the source? Do you trust it? So that's an important aspect as well of big data. And then you would have to look at cleaning it or making it, taking it to a form that it's usable for you. And sometimes there's a fifth V which gets added sometimes, which talks of value. So is my big data generating value? How can I get it to that place of value? Just a quick point here. I mean, if you have any questions, I'll definitely do a Q&A in the end. But in the meantime, feel free to add your questions in the chat window as well. So coming from this whole big data space, how did that start off, or what are the factors fueling big data? I mean, some of the early factors you can say would be around storage getting cheaper. This Backblaze has tracked their costs per GB cost across the years. And it's very interesting if you see this graph on the right-hand side. You will see it's very interesting to see how the cost has reduced over time. I mean, just the gradient of the graph itself can tell you that the cost per GB has reduced over time. And even the sheer numbers of, in 2009, per GB cost was around $0.11. Following that with 2017, where the cost has fallen down to around $0.02 per GB. So that's quite an reduction. And those are some of the factors which could have led to this more data getting generated, stored, and having access to it as well. Other factors would be around IoT, telecom, all of these creating opportunities for data being generated, shared, transported, Cloud is another big factor where you're seeing a lot of the easy access to store, process, analyze data. Um, uh, Another fuel for machine learning would also be processor technology, like the whole movement from GPUs to TPUs. Having access and that kind of processing powers are definitely fuels and factors for um, getting big data, and hence machine learning also uh, prominent and going forward. I mean, these are some of the factors I've listed. I'm sure these are not the only ones. Definitely, but prime among those I would say are these few points here. Now, coming from this big picture of big data, what are the different data types we have and all? If you have to look at data science, what is data science? What all does it capture, right? A lot of time we see a lot of focus, most of the focus is on, say, data modeling or machine learning. But in fact, there is a lot of ancillary items and systems in and around data science, which are just as important, I would think. So I found this infographic, a picture from Simplilearn, which I felt was pretty well depicting the whole data science space. So we can start off with this image, the red arrow right here in the below, the lady with the cup of coffee. I think it could have been any of us sitting there having, enjoying your cup of coffee and looking at what is this next big feature that I want to add into my product. So starting from this red arrow here from this lady, apparently it's at 6 p.m. that all the best ideas strike. And so the next instance, she's here talking with the other stakeholders, understanding how do I get this product into, maybe add this new feature or create this machine learning algorithm. What is the what ifs around it? So that's where, so this is just the beginning, right? I mean, here we are still talking of how do I get started? And that's when the whole journey starts. Data acquisition is one of the important areas as well, one of important steps in getting to a good machine learning model. So first and foremost, do I have the data in-house, or do I need to source it from an external third party, or can I create synthetic data for it? Those are some of the initial questions that you would have to look at and understand before you can get your hand onto the data which can help you move forward. The next step would be data cleaning. So data cleaning is where you're looking at the data and trying to pull out and create, clean it of any dirty data, or so to speak. I mean, real world data is definitely not perfect, and that's which means that you'll have to do quite a bit of cleaning to get to a place where you can use it effectively. So the next step of the process is transformation. So transformation is where you're creating those aggregations or insights, or creating aggregations, or changing it to a place where you can use it. And the next step here, if you can see the exploratory data analysis right on the top. I mean, arguably, I would say this is one of the most important steps in the data science journey, because that's where you're looking at the data and trying to get a grasp of what is your data look like, maybe the spread of the data, how is my data spread out, what are the features available. You would need to do some kind of feature engineering to pull out the right features. So there's quite a bit of depth involved in EDA, exploratory analysis, and that's where, in fact, you could even do POCs or prototypes at this stage to validate your idea as well. So that's from there you would move on to the actual model building, creating your model, deciding the algorithm. You may have decided it earlier on itself, or you might find something better. And moving on to visualization is where you're really talking with, say, the business stakeholders, making sure your model can fit into the system or provides the right kind of insights required. In fact, this step can also be iterative, like you may go back to the EDA after this point and do some tweaking and come back with your model again. But potentially, that's where you're validating your model and seeing if it can be pushed into a deployment stage, right? And from there on, it could go on to deployment. Maybe it fits into another product in a specific manner. So those are when your model is really ready to go out into the world. This is generally a big, insight into the process of data science. In the next few slides, I will, so I'll get into the data modeling, creating the model, the machine learning space itself, into more detail. To start off, if you're looking at some of the basics of AI and ML, I'm pretty sure you have seen this relationship picture of AI and ML quite often. In fact, there are a couple of multiple thoughts in how AI and ML are related, but this particular depiction is quite widely accepted. So what it says here is that ML is a sense subset of AI. Yeah, so AI, I'm sure you have heard these definitions quite often as well. So very briefly, AI is the ability of machines to perform like humans, to behave and perform like humans. And ML is a subset of AI. And here we're trying to get algorithms to learn without actually being programmed. And the last learning type here is deep learning, which is a subset of machine learning. So I won't be talking on deep learning, but very briefly, if you have to understand what is deep learning. So deep learning is actually fashioned behind how our brain works. So in our brain, we have neurons, and these neurons will help you to, you have layers of such neurons. I mean, you have multiple neural layers, which help you to filter out details in layers, and that's how you're able to come out with some kind of an understanding or insight. That's how our brain works. So the deep learning has actually used the same idea or borrowed the same neural network philosophy. And what it does is that you have multiple neural networks, neural layers, which will help you to create an more concrete or detailed analysis or prediction from your initial data. That's a very high level description of deep learning. But yeah, potentially the idea is that as you have more data, like for instance, in the case of image classification, you're trying to understand an image and classify if it's a dog or not a dog, right? So what happens there is that each pixel of your image is a feature, and so that's the amount of data you have. And your deep learning models have to train on really vast amounts of images, vast amount of data to be able to create a accurate enough prediction. And so that's the kind of data scale that deep learning models have to process. And the more layers you have, the more neural layers you have, the better your predictions and accuracy can get. So that's a very brief, quick definition of deep learning. I have a couple of definitions again of machine learning. I won't get into this in detail, but very high level, you can look at it as, in fact, I found this a very interesting example where it differentiates how machine learning is from a program. So in a program, you have, say, data and rules which define what are the answers. Whereas in a machine learning model, you would input the data and the answers, and you would get the rules as the outcome. The result would be a rules. I thought that was a very interesting example or differentiation between programming, the programming world. Yeah. The types of learning, types of machine learning available. You have supervised, unsupervised, semi-supervised, and reinforced. Supervised, as I've mentioned before, is where you have this answers, the right answers, and you have your data, and you're using that, the combination of the two, to create and train your models, and so that in future your model can predict outcomes or predict answers. Some of the performance measures used here are accuracy, and common supervised methods, learning methods, are classification and regression. Unsupervised is where you have, you don't have this right answers, but your system, your machine is trying to make sense of the data, right? An example is clustering, or I mean, the type of unsupervised method is clustering or association rule. I do have examples of classification and clustering through my data set. So I expect it should get more and more clear as we look at those data set and the outcomes around it. Semi-supervised is a combination of the above two. And reinforced learning is where you're using a hit and trial method. Like very commonly in games, when you make the right move, you get points, whereas you get penalized when you make the wrong move. And that's how the system learns. The machine learns to optimize its correct moves, the right moves, so that it can reduce its cost. Any questions so far? I guess not. Yeah, I mean, this is still in the basic introductory slides. Applications of data science. I'm sure you have seen many of these in a lot of the forums and online space as well. E-commerce, a very good use case of data science. Recommendation systems, where the websites are recommending the right ads to the right products for you. Manufacturing is another industry with applications in monitoring, anomaly detection. I mean, some of these are probably across other industries as well, but yeah, primarily more seen in say manufacturing industries. Fraud detection, risk modeling, again, a very common banking use case application. There are some of the more traditional applications as well in algorithmic trading, more traditionally been around for a while. Self-driving cars, we're hearing that a lot all the time. Yeah, I guess that was just a disturbance. Yeah. Yeah, I think some of the more recent applications are coming up in healthcare. And there was one example, one interesting application in healthcare that I heard of recently. So Google actually has been working with a number of healthcare solutions, and one of them was in helping diabetic patients. So what happens is that diabetic patients are prone to have their retina damage, right? They're prone to retina damage. I'm sure if any of you has people with that, you would have witnessed it as well, that you have to keep getting the retina scanned quite often. So the problem was that in a lot of the rural areas, you may not have well-trained doctors who can do a retina scan and determine if there is damage. Or even if you have the trained doctors, there may not be enough of them to move around and do those kinds of detections. So so instead of having a doctor looking at it, what you can do is have a machine learning algorithm. So what they have is an algorithm which scans images and can detect the condition of the retina. So I thought this was a very interesting real world example usage of data science that we're seeing in and around us. So yeah, I mean, definitely the number of applications in data science in healthcare are growing and are getting more and more prominent as well. I guess COVID is another good example where you're starting to see a lot of telemedicine showing up and showing up as well. Yeah. Yeah, I think maybe there was a question, so I can try and look at it.
Aruna, I guess as host, you can mute everyone probably. There is some background coming.
Yeah, okay, sure. Yeah. Just give me a second.
Yeah.
Is it okay now?
So I guess still there's some background noise. Yeah, now it's better.
Okay, yeah. Yeah, thanks. Thanks for bringing that up. Any questions? Definitely feel free to add into the chat window. Yeah, so when you're looking at, so we already looked at high level machine learning, right? The different types of learning methods. We brought up supervised, unsupervised learning methods as well. So within each of them, there are many different algorithms. I mean, what I've listed here is only a subset, very small subset of it. Supervised learning, you have models, algorithms like decision trees, random forest, naive Bayes, and regression methods. Sometimes you can use a combination of these models to create ensemble methods. Besides that, you have unsupervised methods for clustering, k-means, KNN, a prioris, another algorithm. There are definitely many different algorithms here. And deep learning space, you have ANN, CNN, and I'm sure you've seen and heard many of them as well. Besides that, you also have the ability to look at your data through graph analytics. Again, many algorithms which can help and aid you in graph analytics as well. So when you're looking at your data, you also want to see which model really fits my data, which one is giving me the accuracies or the kind of insights that I want to pull out of it. Yeah. So we've seen this supervised, unsupervised before. Besides that, so one of the first thing you want to look at is your the attribute types, like what kind of data do I have? Do I have continuous data, which means that I can use regression supervised methods, right? So continuous data would be, say, income. your income or the temperature. Those are continuous data types. Whereas discrete is where you're looking at, say, identifying whether this belongs to class A or class B. So that's a classification problem that you're looking at. So that's getting that handle around what type of a problem I'm looking at and what kind of data I have is a good first step to determining how do I go from there. So again, if it's discrete and you want to use an unsupervised method, you don't have labeled data, you don't have the right answers which can help you train your model, you can look at clustering methods as well. So that's the high level distinction between the data types and the way you would go about identifying what model to take up. So right here, right at the bottom, there is the structure as well, the hierarchy of machine learning and the different types. I think I see a few questions. I'll quickly take a pause to look at the questions. The first one of the questions I see here is, where do these algorithms fit into the earlier workflow steps which you added? Yeah, so yeah, so you're actually right. I mean, Jeremy, the question is, where do you use the algorithms, right? Definitely EDA, you would want to look at it to see how does my data fit, like what kind of data do I have, what kind of attributes I have, and what kind of a model do I want to pull out. And you can even go ahead and do some initial algorithm, picking up the algorithm, checking how it fits your data, your requirements. EDA, you can also definitely do a POC as well to figure out how it works. And in the next step, when you're actually doing the data model, building your model, definitely that's when you would also be using the algorithm and actually using the algorithm to run it as well. Yeah. I hope that, yeah.
Yeah, so hi, this is Jomi. These methods that you mentioned, such as exploratory data analysis.
Mm-hmm.
So is that not modeling, or is that something else? Sorry, I have no understanding of that. So the question.
Yeah,
But
so it's, yeah. So in fact, I have an example data set. I think that should help you clarify what you're asking. But primarily the idea is that EDA or exploratory analysis is where you're looking at your data and the all aspects around it without really thinking of necessarily how this will look in production. You're just looking at the data, analyzing it. You might even decide to try out a few algorithms to see how it works. Definitely you will do feature engineering, right? What are the right features to use around it? So EDA is the preliminary stage where you're preparing yourself to embark and get into actual full-fledged model, building a full-fledged model. So yeah, so it can be across both stages, but EDA is primarily to understand, analyze, and still exploratory, not necessarily the final.
okay, cool, thanks.
Yeah, yeah. Yeah, so this was just an overview of how would you go about your data set, right? How can you figure out what type of a model it belongs to, what kind of a problem I have, and hence how do I move forward from there? Yeah, so I actually picked this data set from Kaggle, and I thought, considering I am definitely a foodie, this data set really intrigued me or even pulled me. So basically, it's a list of all Indian recipes. It has all the Indian recipes, the ingredients, and a few other information around it. So when I look at this data set very clearly, like a quick look at it, a few things just stood out to me kind of because I understand food maybe so well. Like for one, I have marked this in black here, if you see. So some of these have -1 as prep time. So that looks pretty suspicious to me. I mean, is there a dish which has negative prep time, that doesn't seem possible, right? I mean, that's like kind of the first instinctive thought that you would have looking at, say, a data set like this. Another one is some of these have like 240 minutes of prep time. So that's kind of a very interesting, vast increase, or very different type of an, like a pretty large number, right? The prep time for most of these is around 10, whereas I have some here with 240 minutes of prep time. It sounds a little different or unusual. Another thing is because I know that diet type, I mean, I noticed that I have vegetarian as well as non-vegetarian dishes. And then again, I have different flavors listed here, right? I mean, some of these dishes can be sweet, can be spicy. A quick glance, I can look at this data set. Of course, I have, I mean, this data set was hardly around 2,000 records. So it was easier to look and scan through and get a glance and understanding of it. This is the data set I'm looking at. Now, what can I do with it, right? How do I go to the next step of exploratory analysis? So if, maybe this can answer one of your questions on what is EDA. So EDA is where I'm looking at trying to get a grasp of my data for one, and then I'm trying to then figure out what are the features I can use, what kind of an variations do I see in my data. So it's like, it can be a bit, open-ended to the extent that you can find or figure out or spend as much time as you can in getting a grasp of your data, as well as then feature engineering it and trying out models on it. So in that sense, I did a quick EDA on my data. Like I mentioned, I see that there are non-veg dishes here. So I did a quick check to see how many non-veg dishes I have versus veg in my data set. And then I also did a bit of pre-processing. So I added a total time feature here, which is basically a sum of adds up the prep time and the cook time, right? So I derived that value from the data I have available. Very initial exploratory analysis to see what I have, what can I do with it. Now in the next phase, I start looking at what can I do with the data I have. Is there some kind of a classification I can do with it? So the first thing, being a vegetarian, I was like, okay, let's say I get onto an aircraft, I need to book a meal. Maybe they have a model which needs to determine which dish can go for vegetarian versus non-veg. So that's a very important part. I mean, if any of you are vegetarians, I'm sure you will identify with that problem a big deal. So that's the initial idea I was looking at. Okay, let's say if I have to do a classification of my data, veg and non-veg, how do I go about it? So the first step I have here, like I've mentioned before, is pre-processing, right? So I have to clean my data. I have to add any kind of additional info I need. So I've cleaned my data. I've cleaned and removed some of this weird looking -1s from my data. I've cleaned up where the ingredients were missing. And the next step then was to look at the features. Which of these features can I use to create an model for, right? I mean, I have a number of features, but I decided to look at 2 features which I thought would help me, like flavor. Flavor is it spicy, sweet? Maybe if I know that it's spicy, I know it is vegetarian, because in my previous exploratory analysis, I found that all non-veg dishes were spicy. So I thought, okay, let me try and see if I can just create a model which looks at the flavor profile and says, is this veg or non-veg? On the second phase, I then looked at, say, the ingredients. I look at all the ingredients and then train my model to see if I can identify and predict new data, new recipes, and determine if they are veg or non-veg. So those were the 2 thought processes, initial ideas that I was going with. So using that thought or premise, I looked at what kind of features I can look at. So the first phase I looked at flavors. The second phase I looked at ingredients. So now what I did first is to one hot encode this features. First I started with flavor, one hot encoded it, and then trained my model on it. Now at this phase, what happened is that I used the data that I have, the features I've created, and trained my model and built it, and then run some accuracy tests on it. So I found that the accuracy was not as I wanted it to be. So that's when I went into the next phase, and I used ingredients. So I had to do the same thing again for feature engineering, do a bit of one hot encoding to get to features which I can use for my model. So I think I'll quickly take the two questions that are here. And also if you have any, okay, so you see Maggie, yeah, I mean, definitely number of recipes which can, make us, maybe wake us up as well, yeah. So yeah, so one hot encoding is where you would look at, say, the features and transform it to an form which the models can take in and use and process. So that's so you need to do it so you can run your models. Like for instance, I have flavors as spicy, sweet, right? So in each of these becomes the binary value of 1 or 0 in my features. Each of this becomes a feature and has a binary value, and that's how I get my features around the flavors added into my data set. So that's the data I use for training my model, and based on that, my model is then able to look at a new data input and predict whether it's a veg or non-veg. Now the first iteration didn't work out well. Turns out that flavor is not enough to tell whether a dish is veg or non-veg. Obviously you have a number of dishes which could be spicy, which are vegetarian, many of them which could be spicy and non-veg, right? So obviously that was not the right choice of feature. So in the next set, I looked at, say, ingredients. So I look at ingredients and I could get a little closer to identifying my classification of whether it's a vegetarian dish or a non-veg dish. So potentially at this point, maybe what I have, the model I have, works well for the data I have, for the kind of data I'm looking at. So that was a good first step in analyzing my data and running a classification model on it. But then there are a lot of additional aspects as well, right? I mean, if I was using this model only for Indian food, it could work well. But if I was looking at running it for, say, international dishes, my model may not be able to even identify the ingredients listed there. So that's one thing you want to keep at the back of your mind. I mean, what is the data I'm training my model on? Is it presenting all the different types of predictions that I would be making in the future? Is it well trained in that sense? And then there are also another thing, like I noticed in my data set, there is a lot of vegetarian dishes. So maybe there is bias in my data, right? I mean, maybe the dishes that I have are more biased towards vegetarian. So it may be less, accurate, or may not be able to detect non-veg dishes as well as the other. So those are some of the thoughts that you should look at, some of the actual background of how you would think of when you're applying your model into a real world scenario. So that's one, so this was one angle, one thought process, or one train where we're looking at, say, differentiating veg from non-veg dishes. Another aspect was that let's say I want to create an system where I can tell which of these dishes are close together based on the time it takes to cook them. So I have this website which can recommend dishes for the users, and based on their preference of quick cooking time versus elaborate cooking time, I should be able to pull out and recommend the right recipes for them, right dishes for them. Let's say my problem, the problem that I'm trying to solve here. So in that case, how do I go about it? I do have some information here. I have total cooking time. Okay, so that's the feature or information I'm going to use at this point. What I'm looking at here is some kind of a clustering, right? I mean, I have information with me. I have some information and I want to see how close together are they that they can be called a group. And the group definition is that they have very less distance between within this objects or points. Or the other perspective could be that there is maximal space between the groups themselves. So that's my whole clustering philosophy, or how I'm going to think about clustering. I mean, for a human, it's very easy to cluster. You can just look at this picture and say, all the pinks form one group, all the blues are one group, and hence they are a group. But from a machine perspective, you have to create those simple understandings and definitions of what is a group. So the premise I'm using here is distance. So if the distance is short enough, they form a group. And so using this idea, I then look at my problem of, say, how do I get all the dishes which are similar and hence can be called a group, right? So what I did was, again, getting back to the initial exploration that I'd done on my data, I was looking at a few things. How does my data spread out? How is my data spread look like? So one of the things I notice is that the data has the long tail distribution, or it's also called as the power law distribution. Basically, it's saying that, I mean, a very common example of this is how the wealth is distributed amongst the population. So most of the wealth is with a smaller set of the people. So that's the power law distribution. And we're seeing a similar application or phenomenon here with our data, the total cooking time data. So what we see here is that, so I actually forgot to label the X and Y axis. So the X axis is the total time, the total cooking time, and the Y axis is the number of dishes which fall into the number of dishes, basically, the frequency of the dishes. So on my x-axis, I see that within the 100-minute mark, I see bulk of the dishes fall into this group. Most of the dishes fall into the less than 100-minute mark. And I think that's a good sign, right? Less cooking time for us all. Yeah, but basically that's what I understand from my data spread, that there is a long tail aspect to my data, and there are very few dishes which actually get into the higher ends. So the 700-minute cooking time is really extreme. Out of curiosity, I looked at which is this data sets which have that aspect, and turns out these two are the ones on the bottom. The bottommost two have 620 and 730 minutes of cooking time. But one interesting thing you will notice here is that the Pindi Chana has more of prep time versus cooking time, whereas Srikhand is the other way around. So that's an interesting learning or aspect you look at when you see your data. I mean, at this point, I'm only looking at the total cook time, but maybe in future, if I had to change it or tweak my model, that's something to realize and understand, that they have different prep and cook time as well. So in the next phase, using this learning understanding that of my data, I then looked at clustering my data set on the total cooking time to identify which of the dishes are part of a group or clustered together based on their cooking time that they have. So now the first graph here has 3 colors, red, green, and blue, each of which is one cluster, and they have been clustered together based on their cooking time, the time that it takes to cook them. In this case, I've used K-means clustering, and I've given the number of clusters as 3. Now what has happened is that while the first red and green looks kind of okay, with the blue dishes, I start to see it getting pretty spread out. The range is really large, right? I mean, from almost 400 minutes of cooking time till 700. So that seems like a bit too vast a range. So what I then did in the next phase was to change the number of clusters to 5. And that's how I got this 5 colors here in the lowermost graph. Now this is an interesting because here I now see that those dishes which were taking the most amount of time have now got 2 clusters, which is a bit better because I now don't have too much of an variation in the cook time in these long time consuming dishes. I mean, those are different possibilities, like maybe if you use a different algorithm, you can get slightly different kinds of results. But yeah, in this case, I used K-means, which is looking at the centroid, the central, a center, looking for a center in your cluster, which kind of makes sense because I want it to be as close to a specific cooking time as possible. So that was the whole idea of clustering, to see if I can get identify the dishes with similar cooking time. Maybe I can then choose to label them as red being the least cooking time, pink being slightly more cooking time, and the light blues is elaborate cooking times, right? So I can then use that knowledge that I have gained from my clustering to then apply it to a real world example or an application. So this is a quick look at clustering. If there are any questions, I can quickly look at it. Okay. Yeah, I think that's definitely some applications they're looking at where your Samsung has smart fridges where you can scan through what are the items within your fridge and maybe even get to recipes as well. Yeah. So this was the whole journey we went through right now. We started off with data pre-processing. We explored our data, did feature engineering on it, identified the right algorithm, trained our model, evaluated it. So you can look at parameter training is where I was changing the cluster size. So first time I tried with 3 clusters. I didn't really like the results so much, so I tuned it to 5, and I thought the results were better. I mean, ideally it would be a business stakeholder who would also help you in getting to that place. But yeah, primarily we have done some kind of tuning, retrained a model, and then finally we have a model which can be deployed into a production system or deployed into a application. Now that was a very quick, brief look at a data set and creating insights around it. I mean, this is really a very, so what you have done really is the tip of the iceberg, so to say. There are definitely many things you could do with a data set. You could find different kinds of insights from it. There are many factors also we realized, right? So how well represented is my data? Do I have enough data to apply it for, say, an international audience? Maybe not. What is the bias in my data? Is my data biased towards a specific diet type versus the others, which could then determine how your model will perform in the real world as well, real world application. There are many different aspects in and around it. I mean, definitely many things to look at, evaluate, understand, right from knowing your data to determining the right algorithm, as well as understanding how well represented or what is the quality of your data. So that's where I get then to data quality. I mean, definitely one of the important aspects in defining how your model performs in your model performance will very much depend on the quality of your data as well. So how well represented, is it biased, how consistent is it? So all of those are factors you want to look at before you really have confidence on your model, or you, as you start your data journey, you want to look at what is the quality, understand where it lacks, know as a fact that these are the gaps in it and how will that impact my model as well. Yeah, so that was, with that I come to the last slide. I mean, I very quickly put together the different roles that come around in data science field. I'm sure you have heard quite a few of these. I've picked up two different representations, but I think they're kind of close to what I have seen around. So the data scientist is the one who would be looking at the data and creating the models, whereas a data engineer would probably be the one deploying, creating the infrastructure, looking at the data quality. Machine learning engineer is another role that we see sometimes, which who is helping in productizing the models, scaling them, making them optimal, all of those different areas around it. Business stakeholder is definitely another important aspect of taking a model into a real world application or use case. I mean, this is a very brief understanding or role differentiation. I think I would definitely like to hear from the audience here as well. If you've seen these particular roles, how are they functioning? Like how is it different, or how are they changing in your organization? I mean, quite a few of these are maybe a bit more evolved than the others, but definitely good to hear what's happening in the industry as well. Yeah. So that brings me to the end of my session. So I'm looking at questions here. Does data science also modulate how to procure data? I mean, that's modulate. If you're saying a modulation in terms of what kind of data I pull in, how do I pull it in? Data science, when you say data science, I mean one of the processes in data science does mean that you're looking at your data, modulating it, understanding it. Data quality could be one aspect of modulation. You could create, filters, data quality checks, either through automated tools or systems, which will help you modulate your data and ensure the data you're getting in fits your requirements as well. So Srividya, your question is data quality determination done at the time of pre-processing? Yeah, so I think even Arjun's question is quite similar. So yeah, basically the data quality can be done at the time of pre-processing. Quite often, as you start having real-time models, systems, you can have data quality automated tools and systems as well. Different ways to look at it depends. Definitely, you need to do some amount of minimal data quality checks. And if you're having streaming data, real world data flowing into your models, you should be having data quality checks as well. Yeah. Modulating data quality checks, all of those. Yeah. Any other questions? I guess people can unmute themselves as well now, right? Is it Preeti or Shobita?
Yeah, Aruna. Yeah, so yeah, thank you, Aruna, for the session. So yeah, folks, please go ahead. If you have some questions, you can directly unmute and ask Aruna. Um,
Aruna, when do you see a possibility of AI creeping in?
In what sense?
In the sense of, see, most of the applications that we see is to do with machine learning, with especially data science. Now, with AI applications, especially in healthcare or in predictive analysis, do you see that as a case which is already happening, or in the near future
Yeah.
you would see more of AI also participate in data science?
Yeah, I mean, there are definitely AI applications as well. I mean, how do you differentiate between AI and ML is a different question in itself. There are different ideas and thoughts around it. But very briefly, if you have to look at uh, the ability, so most of the ML models are trained based on the understandings that you have, whereas maybe AI will not have that privilege, right? So probably you can look at self-driving cars as an example. So there are applications coming up. How accurate are they? How well are they meeting the requirements or your accuracy needs could be the question you want to look at. But in terms of ML, machine learning, starting to get more mainstream because you do have a lot of available models which you can use from the various cloud providers. You have data which you can use easily. So that's why you're seeing a more, you're seeing more of machine learning adoption, much more quicker than AI because of the ease of all of these factors involved in it.
Yeah, thank you.
Yeah.
So Aruna, this is Jomi here. Just his question made me think: is like the kind of chatbots and intelligent bots that we're looking at, do they fall under machine learning, like those models that are implemented, or fall under machine learning, or does it is that an AI application? I mean, I never thought
Yeah.
about it earlier like this, but
Yeah,
that
no, yeah, actually, that's a good question. I mean, most of the chatbots we are seeing right now are supervised models, trained models based on, say, let's say you have a customer support use case, you're building it to function and work on your specific customer support team. So most of them are trained supervised learning methods, but you can, some of them do go beyond that where you're looking at, say, creating some additional insights, right? So based on the type of tone you have, or I mean, a number of them also do fall into NLP and methods and learning systems that we already know of. But yeah, you can get to that place where you're going beyond just your trained models and doing what it has been trained to perform and do well.
okay.
Yeah, I mean, maybe I'm not even the right person to answer that because there's a lot of variables involved in that as well, right? I mean, it's not just uh, the model learning or training it, it's also how it will perform on uh, data which is unexpected, which it has never seen before.
True.
I don't know, maybe a quirky question. Now, basically, if I am a company looking to get this done, what phase of exploration should I deploy? Like, should I provide data and expect them to come up with a model? Usually, what are the cases that you see?
Yeah, so there are actually both sides to both methods which have worked and will work, because for one, it could be driven by, say, the product or the features, product management sometimes. So it could be driven by a product requirement or need, which pushes you to start looking at your data to say that how do I create this particular ML feature, or how do I create this insight possible, right? That's definitely possible. The other thing which also happens often enough is that because you've been looking at this data, you're starting to see some kind of possibilities which were never thought of before. Of course, whether it can really make it into your production systems or get into a product depends on how well it turns out and the feature requirements around it. But yeah, definitely both sides have happened and will keep happening as well. Yeah.
Yeah, thank you.
Yeah, thanks. Oh, okay. Any other questions? I guess we have also exceeded quite a bit of the time. Yeah, thanks everyone for taking the time and listening to the session. Shobita, do you want to close it?
Yes, yeah, thank you. Thanks, Aruna. So the session was really insightful. I guess to such an extent that anybody who doesn't have much idea about machine learning or artificial intelligence would have got a very decent idea. I mean, a good thing to start with. The session was really very, very insightful and knowledgeable, I would say. It would have really been helpful for everybody. Thanks a lot for taking your time and, providing this session for leading with members. Yeah, and thanks everybody. Thanks for all the audience who joined. So we have sent the feedback link in the chat. So please feel free to give the feedback about the event. We will try to get it improved. And also another thing is we have an upcoming session on 26th, October 26th, that is on self-coaching and how to improve yourself and how to create a new you. So looking forward to some of your participation there as well. So yeah, that's it from our side. And thanks once again, Aruna. Did you stop the recording, Aruna?